So today we are going to finish our discussion on boundary layers, and in the second hour we'll start discussing laminar flows. So we're still now including the effect of viscosity, and for laminar flows, unidirectional flows in particular, we'll see that actually in that case the inertial term drops out. So we discussed scalings for the boundary layer thickness, and the last thing we discussed was the Blasius solutions. So again, you should be able to go from Navier-Stokes equation to the boundary layer equation, right? So this is when you rescale the y variable with the boundary layer's thickness, which is the square root of mu times x, the location, divided by u. And in there it has this typical diffusing time scale, remember that. So we discussed the solution. We're only going to discuss in detail one solution, and that's the solution for an outer flow which is not driven by a pressure gradient, right? So the boundary layer is the solution when you include the effect of viscosity close to a no-slip boundary condition. Outside, you can still assume the flow to be mostly irrotational, so you can still use potential flow. Depending on the velocity, you know that you might or may not have pressure gradients. And so we're assuming now that we don't have pressure gradients. So that would be typically the case for the flow on top of a flat plate. So if you have the flow on top of the flat plate, then the outer solution, so far away from the boundary, what you have is that your velocity is uniform and is equal to the velocity at infinity. So you have u equals capital U. And we have that the gradient of the pressure in the x direction is equal to 0. Now remember, your gradient of pressure in the y direction, so across your boundary layer, in the boundary layer equation is always equal to 0. So your pressure doesn't change with your distance to the wall, if you want. And so we discussed that you can formulate the solution in terms of a similarity solution. So in terms of a function of a new variable, which is a rescaled variable. And this rescaled variable is just we are rescaling the distance from the wall with the boundary layer thickness, which we derived. And for that, then you reach a nonlinear ODE. So it's an ODE because you just have derivatives of one variable, and it's nonlinear because here you have an f times f double prime. And this is, if at any point in an exam you have a solution like that, so you have an ODE which is not a linear ODE, then I would not, or a very simple ODE, then you should not, you should not think that you can actually solve it. So the solution to that function is here. Let me just show you in the book, but sometimes when it's in the book, people just wonder where it comes from. So this is the solution. Remember that f prime, this is the solution for the Blasius equation. So you were plotting f prime as a function of eta. So when we derived I know, but I think now it's oh no, it's not. It's live. Great. So this here is f prime of eta. And this is eta, and so that is the boundary layer thickness. But usually you're used to thinking about the velocity profile you're using. You're used to think about it as going this way, but you would have to tilt it in your own brain. So I'll show you how you can get to that, and that's maybe for the applied mathematicians here. So this is. Let me go back here. This is an ODE. There are several ways where you could solve that. You have a boundary value problem because you know something at each boundary. You know something at infinity about the velocity, and the value of u also at eta equals 0. And so one method that you can use is called the shooting method, but just so that it doesn't seem so weird where this solution comes from, let me show you how it would look in the program. So it's really, oh no, this is not what I wanted. It's this, yeah. So here, this little program solves this ODE. So here I'm just rewriting the ODE we're trying to solve here. I should have done that. Let me just put up my... Yeah. So we're solving this ODE. Those are the parameters. So A is going to be y equals 0, or the bounds for y. And remember that our solution, we're solving for eta goes to infinity, right? So eta goes to infinity numerically is difficult, so I'm putting eta at 1,000, so this b is just at 100, so this b is supposed to be infinity. And those are our boundary conditions. So we said that f naught is equal to 0, but we are not really interested in f naught. Remember that f the function f is directly related to the stream function, and the stream function is defined to a constant, so it doesn't really matter what I put here. I could put 0, I could put 1 or 2, it doesn't really matter. Now beta equals to 0. This is the value of u at the wall. So this is f0. I'm imposing f0 equals 0, we discussed that. And then we're imposing f at infinity to be equal to 1. Right? So outside of the boundary layer, we want the velocity to match back the velocity at infinity. And the f is just a non-dimensional version of u. So our boundary condition at infinity, if you remember, was f at infinity is going to be equal to 1. So this is our boundary condition here. So gamma equals to 1, and then all of these are just parameters, and then you just write this program, and just so that you're not too scared, most of it is really just plotting, but the program are those 4 lines. You're writing those 4 lines and it solves numerically. So it's using a shooting method. You start from one end of the boundary, you integrate your solution because you have an ODE, and you look how far you match the other boundary condition on the other end. And depending on how far you are, you just adjust how you shot your method to begin with. So I'll just show you that. It runs really quickly. So there's nothing really fancy about this. And I'm plotting it in 2 ways. This is here what we are solving for, right? So we're solving for f prime as a function of eta, but the way you usually think about a boundary layer profile is in terms of you will have y in the y direction, right? And you have the value of u in the x direction. So here, this is you're just flipping the axis between that and this, so you see what the solution really is. But what you're solving for is the function f. And in that case, I'm not plotting f because we don't care about f. We care about the velocity profile, and the velocity profile is in f prime, if you remember the equations. So this is our initial guess. And then you just let it do one shoot. So it started with this slope here, and it shot the solution. And you see that you're not at 1 at infinity. So then it's going to try again. And then as at later tries, it gets closer and closer to 1. And eventually here, you see that it matched the boundary condition at infinity. So it started f prime equals 0 at 0. And you see that f prime is getting close to 1 at, infinity. Here I'm at 20, but the solution is solving up to 100. So you see that there is really nothing to be, at this point, of course, you cannot solve those ODE on your own. But if you had a computer, then it would be quite easy to do. Right? So, I mean, in our day and age, there is not much difference between an ODE which you cannot solve analytically and an ODE which you can solve analytically, because usually you can just solve it with a computer. So that makes it very convenient. So here, this black line now is the velocity profile. Okay, so this is exactly the opposite as what I should have done. This is terrible. Sorry, the axes are wrong. The axes on this plot are the axes of this thing here, right? Let me just redo that. This is sorry about that. Just don't want to confuse you, so I'm going to redo that real quick here. I changed the labels on the wrong plot. So let me redo that. Okay, and now we'll restart because that was a bad demo. So now it should start again. Okay, now. So this is what we are solving for on the left-hand side, right? Exactly. So eventually, just focus on the black profile. Right. This last black profile is the solution when we converged. Note that the equation is non-linear, so you have no choice but to solve iteratively. So it's normal that you have to try a few times before you reach the right solution. So here, black is the solution for f prime, so for the derivative of the f function. You see that it matches the right boundary condition. At eta equals to 0, it's equal to 0, and at eta equals to infinity, so here it's 20, it's equal to 1. Right, so that's f prime. But now if you want to think about how does the velocity profile look inside of the boundary layer, then you have to flip the axis. because here then you have y, and here you have u. So this is how your Blasius profile for the boundary layer looks like, this black curve here. Okay? Note that it's very straight. It looks really like a straight line at 0, and there's a reason for that. And then of course here, then it becomes really flat. At infinity, then you just reach the value of the velocity outside of your boundary layer. Yeah? So this is the Blasius solution. Any question on that? No? Okay, so we'll continue. So there are a few I'm going to oops. Okay, so then we'll discuss a few other definition for boundary layers, and then I'll just pick I'll take my example from the Blasius solution. This was number 4, Blasius solution, and number 5 is going to be boundary layer thickness. And this here is mostly just a library of definitions, because if you read papers, and when you characterize boundary layers, people will refer to certain quantities, and so it's important that you have an idea of what these quantities are. So if I'll just plot here we'll just take Blasius solution, so flow on top of a flat plate as our characteristic example. So I have flow at infinity, which is uniform, right? And we discussed a typical scaling for the boundary layer. Let me just plot it here. And that would be delta, let me call that delta, equal to the square root of mu times x divided by u. Okay, so it looks like a square root function. Now we do know what the Blasius profile looks like. So let me just pull it up here again. Right. So delta x, right? When y equals delta x, that corresponds to eta equals to one. Right? I'm just making sure you guys are following. When I'm at y equals delta, this is the same as looking at eta equals to 1. Okay, so at eta equals to 1, you have to see here when eta is equals to 1, it's going to be around here. So when eta is equals to 1, then f prime is equal to 0.35 roughly. Huh? So you have 35% if you want of the velocity outside of the boundary layer. So let me actually make that maybe a little bit smaller. And so here it's going to be like that. Right, so if I'm here and I'm thinking about plotting my velocity profile, so right here my velocity is 0, and here if this is my velocity 1, so this is u outside. This is u outside here, and this is also u outside. Then here at this boundary layer I will have roughly 35% of my boundary layer. So it's going to look roughly like this. Right, and at delta is equals to x, this here is eta equals to 1, or y equals to delta. And so along this line, essentially you have the value for Blasius solution, you have roughly 0.35 times your velocity outside. If you want, this is what delta represents, right? Now, this could be a good, and now if you're wondering, so what is, knowing the Blasius solution, of course you can plot this velocity profile anywhere, right? You just have to essentially just stretch it by a factor of delta. Right? So if I'm thinking about what is my velocity profile here, well then you have to realize that when you're about that height, and this is when the velocity is about 35% of the velocity outside. So then your boundary layer profile is even more stretched. And here I'm really blowing up the delta which makes it look like the boundary layer is thick, but really the boundary layer is very small. Right? I'm just stretching it because otherwise you can't really see anything. So this is for Blasius solution. Okay, so the first definition for boundary layer is delta 99, and that definition is really easy. It's just defining the boundary layer thickness as the distance from the wall where the velocity is 99% of the outside velocity. Okay, so this is how you define this boundary layer thickness here. So it's the velocity u. So at delta 99, the velocity u at x and at that height, delta 99x, is equal to 0.99 times the velocity outside. Right, so this is maybe a sort of a definition of where your boundary layer starts. If you are underneath that, then your velocity is going to rapidly go to 0, and so you define this as your boundary layer thickness. Now you can look to the Blasius solution. Right, so if I'm looking here, when do I reach 99%? Right, so I would go and try to see where my velocity here is 99%. So it's going to be roughly here. 99% is right there. Right. 99% is right here. So this is 99, and roughly you'll see that you are at 4.92 times 4.92. Right? Eta is equals to 4.92, so y is equal to 4.92 times delta x. Do you see that? Okay, so this is from your solution. So for Blasius, let me put that in blue. For Blasius boundary layer, for the Blasius solution, so this is again flow on top of a flat plate. Then delta 99 is equal to, at x, right, is equal to 4.99 of delta at x, right? Because we saw that 4.92. Right? So this is because we saw that u divided by u was equal to 0.99 when eta was equal to 4.92. So this is what we looked onto the graph, and this yields that. If you look into your book, this is exactly, we just solved it numerically, but this is exactly what your book says also, 4.92. So the fact that we assume infinity to be at 100 is already enough to have a very good solution to the boundary layer. So where would that be? Well, you see here, my delta 99 would really be roughly at 4.92 times delta. So I would have at this point here, let's take this point here, this is 1, 2, 3, 4, 4.99, let's say it's here. So for Blasius solution, this vector here would be 0.99 times the velocity outside. Yeah? So this is the definition of the delta 99 of boundary layer thickness. Then there is another boundary definition for boundary layer, which has to do with mass conservation. And this is the displacement thickness, which you will find written either delta star or delta 1. And this is called the displacement thickness. So for the displacement thickness, you have to look at the following picture. So let's say that I'm looking at everything in a 2D planar geometry. And I'm just going to imagine a boundary layer profile, which looks like that. Right, let's say this is my boundary layer profile, and the velocity here is u. Right? If you had an ideal flow, so if you this is Blasius solution, right? If you have the corresponding ideal flow where you neglect the effect of viscosity, then the velocity is u everywhere, right? So then if I have, this is with the effect of, now this is when you have a real boundary layer, so you include the effect of viscosity and you do have a no-slip boundary condition. But if you had an ideal flow, then the velocity would just be u everywhere. Right, so you would have a flat profile. It would be just u everywhere. But now you see that if I went to u, if I had u up to the wall, then I would have more mass. Then essentially what is unphysical is that here I actually have more mass flux in this case than in that case. Right? You have a mass deficit because of the presence of the boundary layer, because of the no-slip boundary condition. So the displacement thickness corresponds to, like, characterizes this mass deficit, right? And if you want the physical picture, is by how much would you have to raise your boundary to get the equivalent mass flux. Right? So if you here raised your boundary, let me do that in blue, by delta 1 to delta star, then you would have the same mass flux, okay? Or you can actually characterize that your mass deficit is going to be u times delta 1. That's the definition of the displacement thickness. So your mass deficit due to the boundary layer is equal to delta star or delta 1 times u. Okay. That's essentially the definition for delta star, and this you can do as an exercise. That's a good exercise to get back into control volumes. It's a mass conservation problem. So as an exercise, just verify that delta star is equal to the integral from y equals to 0 to infinity of 1 minus u divided by the velocity in the outer layer dy. Okay, so that's the definition for the displacement thickness. Now note again that this integral, sorry, I can't calculate for the Blasius layer. I have u. Yeah? From my solution to Blasius, I have the velocity u at every y for every given x position. So you could compute this quantity to get the boundary layer thickness, the displacement thickness for Blasius solution, and this solution, this value is 0. I don't know by heart, 1.72, 0.72. Now that would be a good example, a good assignment for you to use the routine that you have now, to actually verify that this is indeed the displacement layer, the displacement thickness for the Blasius solution. So for Blasius solution, delta star and x is equal to 1.72 times delta x. Remember that delta x is the square root of mu x divided by u. So this is to do, this is as an exercise. Verify this. Verify the 1.72 from the MATLAB routine. Okay, again, from the MATLAB routine, if you integrate between 0 and 100, that will be enough. You should be close to that 1.72. You don't have to integrate to infinity, because otherwise you need the solution to infinity. Okay, so this is another definition for the boundary layer thickness, and another characteristic thickness will be the momentum thickness, which will be called usually theta or delta 2. And for there you have to, it's essentially the same picture, right? When you look at the real solution, so say again, this is flow above a flat plate, so I have a solution to my boundary layer profile, which is the Blasius solution. If I'm looking at an ideal solution, you also have, so you see that you have a mass deficit. But if you think about the momentum coming into any control volume, into your boundary layers, so if I'm taking a control volume like this, for instance, right, any cross section, and I compute the momentum influx, then you also have a momentum loss. You have a momentum deficit, and so you will see, just if you do the exercises. You will see that it's not the same as the mass deficit, right? So the momentum thickness will be the same. It's by how much do I need to raise this this wall here to have the same momentum flux, and you will see that the momentum thickness by definition will be the integral from y equals 0 to infinity of u divided by capital U times 1 minus u divided by capital U. Actually, to do this one, you just need to go back to a homework, because it was one of the homework problems when you practice control volumes. So if you don't remember how to do that, how to show this, then just go back to the homework. So here theta will correspond to the characterizes the thickness that you would that you would need to raise the wall in order to have the same momentum flux. So it characterizes the momentum deficit. Again, this integral, because you do know for Blasius solution you would know u, you can characterize what theta is, and so for the Blasius solution theta is equal to for the Blasius solution theta of x is equal to 0.664 of our typical scaling for the boundary layer. Okay, this is for Blasius solution. So if I'm going back to my original plot, right, just depending on really what you're characterizing in your flow, you define different boundary layer thickness, right? So here, the one I plotted here is just our typical scaling for the boundary layer, right? Now, delta 99 would be, roughly here. That would be delta 99 for Blasius, for the Blasius solution. The momentum thickness is 1.72. So here I have 1, I have 2, so roughly here. So it's 1.72 eta, so it's roughly 2. So it'll be here, here it's there. And this would be delta star. And for Blasius, the momentum thickness theta is 0.64, so it's roughly one half of that. So it's here. And the definition you would use for the boundary layer thickness depends really on the problem. It depends on what you're looking at. If you're looking at mass, then of course you would look at delta star, momentum. You saw actually in your homework that the momentum thickness also characterizes the drag onto the plate, right? So depending on what you look at, you may use different definitions, and so it's important that you sort of know what these are. Okay, any question on this? Yeah? So this is 4.94, the Blasius solution.
Yeah.
Right?
What is delta x initial?
Delta x? Yeah, I mean, you could define delta x just as, it's just one definition for the boundary layer thickness. And in that case, it like we took it directly from the diffusion, from the scaling argument on the diffusion length. But that's sort of random. You know, why do I call this the boundary layer? And we saw that for Blasius, that corresponds to, you could define it as, you know, this value for delta x corresponds to the point, the thickness or the height above the no slip boundary, where the velocity is equal to 0.35 times the velocity outside of the boundary layer. Like, why would you take that as your definition? Why not 0.3 or 90% or 99%? Right? So as a convention, you would say, well, you know, like where the velocity, if I'm outside of you could define, you know, that you're outside of your boundary layer, if the velocity is higher than 99% of the velocity outside. Then I'm really outside of my boundary layer. That would be the definition for delta 99. But then physically, there are other, you know, measures of, you know, the effect of a boundary layer, the effect of the no slip. One of it is a mass deficit. Right? If you compare it with the ideal flow, so then in that case, the definition that arises is the one for the displacement thickness. If you're looking at momentum, then you have another. Then there is another definition for the boundary layer thickness that arises, and that is the one for the momentum displacement, the momentum thickness. Yeah. So all of these are very arbitrary, but those are the ones that in papers, even on turbulence and everything, those are the ones that you will see come again. Yeah. I think the delta 99 is the one that you would see quite often when you're qualitatively describing the velocity profile, because it sort of makes sense. You know, why 99 and not 99.9? I don't know. That's just how people defined it, right? Essentially, your boundary layer is really below that delta 99. You're really in the boundary. You're outside of this delta 99, so you're really outside of your boundary layer, right? Because the velocity is so close to the velocity at far above your no slip boundary condition that you don't really see you don't really have direct effect of the no slip anymore. Yeah. Okay. Any other questions? So those are just definitions that you need to know. Right? But the one for the mass, the displacement thickness and the momentum thickness, they also have like a control volume analogy behind, and they have a physical meaning. So it's important that you're also able to, that you should be able to do those analysis to get back to the definitions. So to link the graphical definition to the mathematical definition. So the last thing we are going to discuss is boundary layer separations. Now, as you have noticed, the solutions we are looking at now, they're a bit more complicated than potential flows because we don't have any analytical solution. But they still represent very important physical phenomena. So it's important that you can follow this and understand that. Boundary layer separation. So what the boundary layer we've looked at is, when we derive the Blasius solution, is the boundary layer along a flat plate, right? And you present the boundary layer on top of a flat plate because, remember from the ideal flow, if you just have a flat plate, then your velocity is uniform, your pressure is uniform, you don't have any pressure gradients in the x direction, right, or in the streamwise direction. So the Blasius solution is really only valid for a flat plate. When delta dp over dx, let me stress that, when dp dx is equal to 0. And now you know that as soon as you will have curvature, like a boundary, like on an airfoil, or if you have a flat plate at an angle of attack, then the velocity field is affected, right? And in that case, there will be pressure gradients. So if you just think of a real situation, let's think here on the upper surface of an airfoil. I'm just looking here, or this is the top of a cylinder or anything. Now it's curved. Right. Here it's curved. Let's think, for instance, this is our small schematic, flow around a cylinder. When the flow is coming, this is we're discussing the ideal flow. So I'm thinking of what is happening outside of my boundary layer. Right? You know that here you have high pressure because you have a stagnation point. Here you also have high pressure, and here you have very low pressure. Right? You have very low pressure. So if you're thinking about what does the pressure do along this boundary, well, here the pressure decreases, and here the pressure increases. And I'm talking about the pressure outside of the boundary layer. So let's say that what would happen on this top here, if I represent it here, is that here dP dx would be negative. The pressure decreases. It goes from the stagnation point to where the pressure is much lower. So the pressure really drops. And after that little hump, dP dx increases. Right? Again, I'm putting a straight derivative here to highlight the fact that partial p over partial y is equal to 0. So p is not a function of y. In the boundary layer. Outside of the boundary layer, it is. Right? It could be. But here we're talking about the boundary layer. So let's think about the boundary layer here. What we'll briefly discuss what effect has this pressure change in the s direction in the outer region. What effect does it have on the boundary layer itself? Right. For the Blasius solution, this dP dx was equal to 0, so it doesn't really it didn't come in, but it actually has an important effect, and in particular it has an important effect on separation. So let's rewrite the x momentum equation Let's rewrite the x momentum equation of the boundary layer. So the inertial term remains unchanged. So u partial x plus v partial u partial y with a rho is equal to minus partial p over partial x. And in the boundary layer, it is a straight d, because p is not a function of y, plus I only have one term left in the Laplacian term, in the viscous term, is second partial of u with respect to y. So at the wall, at the no-slip wall, I have a no-slip, so u at x and y equals 0 is equal to 0, and v at x and y equals 0 is also equal to 0. Right. So if I'm writing, it's very rare that I will do that, but here I'm writing the PDE at a particular point. So if we are rewriting the x momentum equation at a particular point, so at a point x and y equals 0, then from the x momentum equation I have that 0 is equal to minus partial p over partial x plus mu second derivative of u with respect to y. So if we rewrite that, we get information about the curvature of the velocity profile. Right, so we get that second partial of u with respect to y is equal to 1 over mu partial p over partial x. So let's think about the first part of the, the front of the what's happening more towards the leading, not really the leading edge, but the front side of the cylinder, when the flow is accelerated. When the flow is accelerated, the pressure drops. Right. So this is when dP dx is equal to 0. The outer flow is accelerated. Right. In that case, we have that the second partial of u with respect to y is negative. Now what does that mean? Just think about a parabol. Right? The second partial is essentially the coefficient of your parabol. So the coefficient in front of the monomial in front of the x squared is negative. So you know that the graph of your curve, if you're just thinking about plotting u as a function of y, that means that y equals 0, the graph of your curve has a curvature like that. Right? Has a curvature like that. It doesn't have to really bend all the way over. So let me just say that it has a negative curvature. Okay? Think about x equals to minus y squared. Right? X equals to minus y squared. The derivative of that is just the second derivative will be minus 1. So when the second derivative is negative, then the graph goes like that. So if you're thinking about the velocity profile, so the velocity profile really you just flip the axis when you think about that, then initially it goes like this, and that's fine because later on you know that it's going to go to a uniform velocity. So this is that curvature here. Okay? This is the shape of your velocity profile inside of your boundary layer. So let me mark that on our plot here. So when delta x, oh actually I'm going to redo this plot, but down there on this page, because otherwise I'm going to have to go back and forth. So let's assume we have a curve, but it's, let's say this is let me just say this is flat, but here dp dx is negative, and here dp dy is positive. Okay, so the curvature is so small you can't see it. And so far, when dp dx is equal to 0, then my profile is going to look like this. My boundary layer profile. Right? Now there is a dp dx, so of course the Blasio solution is no longer valid, but everything that we discussed about the Blasio solution and the boundary layer thickness is still sort of not going to be dramatically different, let's say. Right? So you still have that your boundary layer increases with x, for example. Right? We still have a boundary layer increasing, so if I was really far downstream, then I would have more of a profile like that. As I increase and I get closer to here, right, my profile is becoming more, my boundary layer thickness is increasing. So I do have also an increase here of my boundary thickness. Right? This is when delta p is equal when the gradient is negative. And actually this is not really clear, but it looks like it's linear, but here I really have a curvature to that curve. Okay? Like that. So this is when dp dx is negative. Now let's look what happens when dp dx is positive. So this is on the other side of the cylinder, when the flow now, the flow initially was accelerated, and now the flow slows down. Right? You are on top of the cylinder where the pressure is really low, and you're moving towards the stagnation point at the back of the cylinder where the pressure is high again. Okay, so the flow here, the velocity is high, and the flow now, the flow velocity decreases, and dp dx is positive. So here dp dx is negative. So let's look what happens when dp dx is positive. So we just do the exact same analysis that we just did, and it will not surprise you that in that case the second derivative of u with respect to y is going to be positive. Let me just move that here. A bit more space. Good. Okay, so the second case is dp dx positive, so the pressure increases. Pressure increases means that the velocity, the flow decelerates, and I'm really talking about the pressure in the outer flow region. And the outer flow in this case is decelerated, slows down. So then the second partial of u with respect to y is positive. So then your curve is going to have the opposite curvature. So you expect it to turn this way, right? Now what does it mean when you look at the velocity profile? That means that your velocity profile is going to initially have a curvature like this. But then you know that you need to reach u, so you know that your curvature profile is going to look something like that. And in particular, you know that somewhere in here there will be an inflection point. Yeah? So now your curvature is different, right? I made it a bit dramatic here, but essentially what you will have is that later on, when dp dx is positive, then you will have an inflection point into your curvature profile. So at first, it might look like that, your curvature profile. Right? But you know that the boundary layer thickness increases, so the slope here at the wall becomes lower and lower, and eventually what you might get is something like this. Right? So at some point what you might get is that you have an inflection point, and eventually you might even have an inversion of the flow. Right? Because you have that negative, that positive, it depends on your units, but positive curvature for u as a function of y. Right? So here, somewhere in there, when the velocity changes direction, you have a stagnation point, and as much as your streamlines here, they will look like this. Here they will go in this direction, and you're going to have flow reversal and detachment here. So the pressure outside, if you have, and you know that, right? Once you include the effect of viscosity, we never expected the solution for the flow around a potential, for the potential flow around a cylinder to be really valid. We do expect somewhere detachment, but now you see where it originates. Right? It originates from the change, from the inversion of the pressure gradient. When your pressure gradient becomes positive, so your pressure starts to increase, when your flow slows down, then the effect of viscosity, your boundary layer effects, will tend to create a stagnation point, and then you will have flow reversal, and the only way that you can satisfy mass conservation is if you have separation, boundary layer separation. Okay? So, and of course, the more severe this delta P, delta X is, so the more severely, the more quickly, when this is a sharp gradient, that means that the pressure really quickly increases, or if you think your velocity quickly drops, the more severe that is, the more dramatic the separation will be, the earlier it will happen. Right? So essentially, when we're discussing conformal maps and stuff, what people initially, what they were focusing on developing those NACA profiles was developing profiles with high lift but where the pressure drop, where it reaccelerates, right? So after the leading edge, then the pressure is going to increase. So initially the pressure decreases at the leading edge, but then it re-increases. They would focus on developing airfoils where the pressure increase will be very gradual, where the flow would not suddenly decelerate, because sudden deceleration usually leads to separation. Okay, so this is what they were trying to optimize for. So you see it here, right? When this dpdx is big, that means that, just use Bernoulli, that means that your velocity decreases very sharply. Right? When the pressure increases, your velocity decreases very sharply outside of your boundary layer. When this happens, then you are at big risk of separation. This is when the flow separates. You see it from here. Okay? Now that's the last thing I wanted to discuss for boundary layers. So everything which I covered here, I expect you to know for the exam. Some discussion. This discussion, of course, is not really a quantitative discussion; it's a qualitative discussion. But you need to understand that. Okay? Any questions? Oh, I went over time. Yeah.
Can you explain what you denoted with the green line there?
No, well, so here I don't. This is very qualitative because I don't have a solution. Right? You could compute the solution to your boundary layer, but then you would need numerical code. So I'm just representing a hypothetical boundary layer. Right? What you have here, when dpdx is very positive, right? Then you have a very big curvature in this direction. Right? Yeah. So at some point, because you have an inflection point, right, you do have an inflection point here. What's going to happen is that this slope is going to become infinite, if you want. Right? At that point, essentially, you have separation. If you solve for your boundary layer equations further to on the other side of that point, then you would see that initially the velocity is actually negative. And you would have something like this. Yeah? So now if you follow where the flow is coming from, that actually tells you that you have a separation point from mass conservation. Like a simple argument on mass conservation tells you that you have a separation point. You have mass flowing in here, and you have mass coming in here. The only way you can solve mass if you have a detachment of your boundary layer. At that point you have separation. Yeah? So the more gradual the flow decelerate, the more likely the flow is going to remain attached. If it decelerate really drastically, then you're going to have immediately separation. Yeah? Okay, I'm a bit over time.